Evolution of the graphics processing unit. The modern computer graphics pipeline is the result of decades of intense architectural experimentation aimed at solving a singular, mathematically exhaustive problem, manipulating millions of pixels on a screen dozens of times per second. In the earliest days of computing, the central processing unit, or CPU, was responsible for every task a computer performed. The CPU ran the operating system, processed user inputs, executed game logic, and painstakingly calculated the color and position of every single pixel sent to the display monitor. Because the CPU is inherently a generalist, designed to handle a wide variety of serial tasks sequentially, forcing it to act as a dedicated graphics painter created a severe computational bottleneck. When the CPU was busy drawing a complex background, the entire system would slow down, resulting in sluggish frame rates and simplistic visual fidelity. Solving this bottleneck required a fundamental rethinking of computer architecture. Hardware engineers realized that they needed to create specialized silicon dedicated entirely to visual processing, relieving the CPU of its most tedious labor. The earliest paradigm shifts in alleviating the CPU bottleneck were driven by pioneering hardware engineers like J. Miner, who spearheaded the development of custom video circuitry. In the late 1970s, the Atari 2600 home console utilized a video shifter known as the television interface adapter to generate its video signals, marking a rudimentary step toward hardware graphical assistance. However, a far more significant leap occurred in 1979 with the introduction of the Atari 8-bit computer line, which featured the alphanumeric television interface controller, commonly referred to as ANTIC. ANTIC was effectively a dedicated video microprocessor that functioned as an early precursor to the modern graphics pipeline. Unlike previous systems that forced the CPU to manually push data to the screen, ANTIC processed two-dimensional display instructions independently using direct memory access, meaning it could fetch data directly from the system's memory without interrupting the main processor. Furthermore, rather than relying on a rigid, contiguous frame buffer, which would require large amounts of prohibitively expensive memory, ANTIC operated by interpreting a specialized program called a display list. This display list was a sequence of hardware-level instructions that told the ANTIC chip exactly how to map memory to specific bit-mapped or character modes as the television monitor's electron beam swept across the screen. The controller was programmed with a specific mathematical logic to minimize memory usage. For example, the value of empty background scanlines was derived by a formula where the system subtracted 1 from the total desired lines and multiplied the result to quickly flood the screen with background colors, entirely bypassing the CPU. Additionally, programmers could utilize instructions like the load memory scan to tell the chip exactly where screen data was located, and the jump while vertical blank instruction, which commanded the ANTIC chip to loop back to the very beginning of the display list once the bottom of the screen was reached. This automated the rendering cycle and allowed for hardware-driven smooth scrolling, establishing the philosophical foundation of modern graphics hardware, offloading highly specialized repetitive display tasks to a dedicated coprocessor. This philosophy of hardware-level offloading reached an extraordinary level of sophistication in the mid-1980s with the release of the Commodore Amiga. Introduced in 1985 and designed largely by the same engineering talent that created Atari's custom chips, the Amiga differentiated itself radically from competing 16-bit systems like the Atari ST and the Apple Macintosh. While its competitors still forced the CPU to draw graphics entirely in software, the Amiga utilized an advanced custom chipset paired with a unified memory architecture known as ChipMem. ChipMem allowed both the Motorola 68000 main processor and the custom graphical chips to access the same pool of memory, eliminating the latency of transferring data between isolated components. The Amiga's graphical dominance relied heavily on two revolutionary custom chips, the copper and the blitter. The copper was a specialized coprocessor whose sole purpose was to synchronize perfectly with the sweeping electron beam of the cathode ray tube monitor. As the beam moved down the screen, the copper could execute its own display lists to alter color palettes or change video resolutions mid-scan line, executing these visual changes instantly without demanding any attention from the CPU. Working in tandem with the copper was the blitter, an incredibly powerful dedicated circuit designed exclusively for the rapid movement and modification of large blocks of memory. The term blitter originated from the bit block transfer operations pioneered by the 1973 Xerox Alto computer. When a video game needed to move a character sprite across a background, earlier systems required the CPU to fetch and decode short loops of load and store instructions, analyzing every single pixel. The Amiga's blitter, however, executed these memory manipulations in parallel with the main processor. It was capable of handling complex operations natively in hardware, such as processing data that was not byte-aligned, and managing transparent pixels through cookie-cut masking, ensuring that a moving character did not overwrite the background scenery with an ugly solid box. The blitter even featured hardware-accelerated mode for drawing geometric lines using the Bresenum algorithm. A programmer merely had to define the mathematical octant trajectory, and the silicon would draw the line instantly. Because the blitter handled this heavy lifting, advanced two-dimensional graphical operations that crippled other computers were effectively free on the Amiga, allowing it to dominate the multimedia landscape and fostering the birth of foundational 3D rendering packages like Lightwave 3D. While Commodore and Atari pursued highly customized proprietary silicon that locked developers into their specific ecosystems, the IBM PC-compatible market was moving in a fundamentally different direction. IBM prioritized broad standardization over specialized coprocessors, a strategy that would ultimately lay the groundwork for the modern add-in graphics card market. In 1987, IBM introduced the Video Graphics Array, universally known as VGA, alongside its PS2 line of personal computers. VGA was not a custom Blitten chip, rather it was an analog interface standard and a display hardware specification that dictated exactly how video sources linked to display monitors. It standardized the ubiquitous 15-pin D-sub-miniature connector, characterized by its blue housing and 3 rows of 5 pins, which became the global standard for monitor cables for decades. Furthermore, it established strict baseline resolutions and color depths, most notably supporting a crisp 640 by 480 pixel resolution, or alternatively a lower resolution that supported an unprecedented 256 colors on screen simultaneously. The true historical impact of the Video Graphics Array was that it became the lowest common denominator for the entire computing industry. Because the VGA standard was universally adopted, it allowed third-party hardware manufacturers to consolidate the previously massive arrays of discrete graphical circuitry into streamlined integrated chipsets. Prior to this standardization, graphics cards were massive, full-length circuit boards filled with over 200 discrete components. Following VGA, manufacturers could shrink this footprint down to just 1 or 2 controller chips supported by a small amount of memory, reducing the component count to as few as 15 pieces. This immense consolidation drastically lowered manufacturing costs and catalyzed the transition into the Super VGA era, providing a stable, unified architectural foundation that the impending three-dimensional graphics revolution would desperately need. As the 1980s gave way to the 1990s, the visual frontier of the technology industry shifted aggressively from manipulating flat two-dimensional bitmaps to simulating fully realized three-dimensional geometric spaces. Simulating a 3D world on a flat 2D screen requires immense mathematical calculation, specifically matrix multiplication and floating point geometry. Personal computers of the early 1990s lacked specialized hardware for these mathematics and were forced to rely entirely on software rendering. During software rendering, the main CPU struggled to manually calculate the geometry, divide the perspective, and rasterize the pixels, resulting in blocky, untextured shapes and painfully slow frame rates. Consequently, the first true pioneers of 3D hardware acceleration were not home computers, but massive, expensive arcade machines. In 1988, Namco unveiled the System 21 arcade board, internally dubbed the Polygonizer. Designed specifically for 3D polygon processing, the System 21 utilized an array of Motorola processors paired with multiple Texas Instruments digital signal processors, or DSPs, which were dedicated exclusively to performing the complex 3D math. This hardware achieved a level of geometric performance that dwarfed the capabilities of consumer PCs, powering early 3D hits like Winning Run and Starblade. Sega followed shortly after with its Model 1 arcade board in 1992, utilizing hardware concepts directly derived from military-grade flight simulators. These towering arcade cabinets proved definitively that dedicated mathematical coprocessors were the key to unlocking fluid, immersive 3D graphics. The transition of this high-performance 3D graphics technology from multi-million-dollar flight simulators and coin-operated arcades into the average home personal computer was catalyzed by the founding of 3DFX Interactive in 1994. The company was established by Scott Sellers, Ross Smith, and Gary Tiroli, three engineers who had previously worked at Silicon Graphics, a legendary technology firm known for building ultra-high-end graphical workstations. Their collective experience at Silicon Graphics was highly formative, teaching them how to engineer hardware that prioritized raw rendering speed. Leveraging this background, the 3DFX team engineered a consumer-grade chipset that brought workstation-quality graphics to the home PC market. In 1996, the company released the Voodoo graphics accelerator. The Voodoo architecture was highly unique. It physically separated the rendering pipeline into dedicated chips, primarily utilizing a frame buffer interface to handle the screen output and a dedicated texture mapping unit to seamlessly wrap graphical images around bare 3D polygons. Because the engineers understood how to cut the right corners of the graphics pipeline without impacting visual quality, the Voodoo card sustained unprecedented performance metrics, processing 30 million bilinearly filtered textured pixels per second. However, the original Voodoo card was strictly a 3D accelerator. It lacked a standard 2D VGA controller entirely, requiring the user to install a physical pass-through cable bridging the Voodoo board to their existing 2D video card. A critical component of 3DFX's absolute dominance in the 1990s was the introduction of its proprietary software interface known as the Glide API, created by the company's first engineer, Brian Hook. An application programming interface serves as the crucial translation bridge between the software code of a video game and the physical hardware of the graphics card. During the mid-1990s, the established industry standard for 3D programming was OpenGL, a powerful but heavy library originally designed for scientific workstations, while Microsoft was attempting to push its own standard known as Direct3D. Early iterations of Microsoft's Direct3D were widely criticized by developers as convoluted, sluggish, and bogged down by hardware abstraction layers that severely limited performance. Recognizing the desperate need for speed, 3DFX designed Glide as a streamlined, highly focused subset of OpenGL. Glide explicitly stripped away extraneous workstation features to focus purely on the functions required for high-performance video games. More importantly, Glide mapped directly to the native instruction set of the 3DFX silicon. This meant that games programmed for Glide bypassed the cumbersome operating system layers, delivering a close-to-the-metal performance that competing cards from ATI and Matrox simply could not match. Consequently, Glide became the de facto standard for PC gaming, ensuring blockbuster titles ran with unparalleled fluidity and visual fidelity when paired with 3DFX hardware. However, the technology sector is notoriously unforgiving, and the reign of 3DFX was surprisingly brief. The company's rapid decline was precipitated by a series of strategic missteps and a shifting software landscape. As Microsoft heavily revised and improved Direct 3D, making it an efficient, universal standard that worked across a multitude of different hardware configurations, the necessity for a proprietary hardware-locked API like Glide began to evaporate. Game developers increasingly favored open standards like DirectX and OpenGL because they allowed their software to reach the widest possible audience without alienating consumers who owned competing hardware. Simultaneously, competitors like NVIDIA began releasing graphics cards that successfully integrated both 2D processing and 3D acceleration onto a single high-performance chip, eliminating the need for the clunky pass-through cables that 3DFX still relied upon. 3DFX stubbornly depended on its aging Voodoo core architecture for far too long, failing to implement critical modern features like 32-bit color depth and advanced stenciling. After launching the delayed and overpriced Voodoo 4 and Voodoo 5 series, 3DFX found its market share entirely eroded. Facing insurmountable financial difficulties, 3DFX filed for bankruptcy in late 2000, and its assets, patents, and engineering teams were acquired by its fiercest rival, NVIDIA. As the industry approached the new millennium, 3D graphics accelerators had successfully conquered the process of rasterization, which is the act of converting three-dimensional geometric data into a two-dimensional grid of colored pixels. However, the computer's main processor was still heavily burdened. In the standard graphics pipeline of the late 1990s, the CPU remained entirely responsible for the complex mathematical calculations required to construct the geometry of the 3D world and to determine how light interacted with those geometric shapes. Because a CPU is a general-purpose processor, its floating-point math capabilities were severely strained by the demands of advanced graphics. Furthermore, while CPU speeds were doubling roughly every 18 months, the demand for graphics processing power was increasing at an exponentially faster rate, advancing 8 times as fast in the same period. This created a severe computational bottleneck. No matter how fast a graphics card could draw pixels, it was forced to wait idly while the CPU struggled to calculate where those pixels should go. This massive structural bottleneck was shattered in the fall of 1999 with the release of the NVIDIA GeForce 256, an architectural leap that fundamentally altered the trajectory of the computer industry. The GeForce 256 was such a monumental departure from previous 3D accelerators that NVIDIA coined an entirely new term to describe it: the Graphics Processing Unit, or GPU. To qualify as a GPU, NVIDIA defined the hardware as a single-chip processor that integrated transform, lighting, triangle setup, and rendering engines directly onto a single silicon die. The primary technical significance of the GeForce 256 was its inclusion of hardware transform and lighting, commonly abbreviated as T&L. Prior to this moment, hardware T&L was an exclusive feature found only in professional multi-million-dollar graphics supercomputers. Bringing it to the consumer PC market required overcoming immense manufacturing cost barriers. To truly understand the magnitude of the GeForce 256's introduction of hardware transform and lighting, one must first understand the staggering mathematical complexity involved in simulating a 3D environment. A highly effective analogy for this process is the production of a live-action theatrical film. In this analogy, the transform stage of computer graphics functions remarkably like the film's director and staging crew, who are responsible for precisely positioning the actors, the props, and the camera within a physical space. In a virtual computer world, every single three-dimensional object is constructed from a wireframe mesh of microscopic coordinate points, known as vertices. The hardware transform engine is responsible for executing complex mathematical matrix multiplications to translate these vertices across several different spatial coordinate systems. First, the engine calculates the position of the objects in world space, which represents the absolute physical layout of the entire virtual environment. Next, it translates those absolute coordinates into eye space, calculating how the scene appears relative to the position of the virtual camera. This specific translation allows the hardware to perform clipping and culling, mathematically identifying and removing objects that are currently located behind the viewer, ensuring the computer does not waste precious processing power drawing things the player cannot see. Finally, the transform engine projects these refined coordinates into screen space, flattening the three-dimensional depth into a two-dimensional grid format that can be output to a physical monitor. Because a video game is a moving, interactive medium, every single vertex of every single object on the screen must undergo this complex 4x4 matrix multiplication every single time the scene is redrawn. If the transform stage operates as the director of our virtual film set, the lighting stage functions as the production crew's gaffer, tasked with configuring the ambient illumination, the spotlights, and the color gels to create a realistic, immersive atmosphere. Prior to the GeForce 256, the central processing unit was forced to calculate how light interacted with surfaces, severely bottlenecking performance. The GeForce 256 revolutionized this by featuring a discrete, dedicated hardware lighting engine that operated entirely separately from the transform engine to guarantee maximum computational efficiency. This dedicated silicon continuously calculated distance and direction vectors from virtual light sources to the three-dimensional objects, and subsequently from those objects to the perspective of the viewer. This allowed the hardware to perform real-time calculations for both diffuse and specular lighting. Diffuse lighting models the behavior of light that scatters equally in all directions upon hitting a rough surface, much like natural sunlight hitting a brick wall. Specular lighting, however, is far more computationally demanding. It calculates mirror-like properties, such as dynamic glare, reflections, and bright highlights that shift continuously as the viewer moves their perspective relative to the light source. Because specular lighting is inherently dependent on the viewer's exact real-time position, it cannot be pre-calculated onto a static texture. It must be resolved flawlessly in real time, a task the GPU's dedicated matrix math engines handled effortlessly compared to a standard CPU. By moving these intensive transform and lighting calculations from the CPU to the dedicated hardware of the GPU, the industry experienced an immediate and staggering performance uplift. General-purpose CPUs were highly inefficient at continuous matrix mathematics, whereas the GPU's dedicated engines were optimized specifically for these exact floating-point calculations. Consequently, the GeForce 256 could process transform and lighting mathematics at 2 to 4 times the speed of the fastest CPUs available at the time. This massive surge in processing power allowed game developers to employ much finer tessellation, which is the process of converting mathematically curved surfaces into tiny flat polygons. By offloading this immense task to the GPU, developers were able to increase polygon counts by a factor of 3 to 5, smoothing out jagged edges and enabling the creation of highly detailed organic characters and lifelike environments without crippling the frame rate. Just as importantly, migrating TNL to the graphics card completely liberated the computer's CPU, no longer held hostage by the relentless demands of geometry and lighting math. developers could finally utilize the CPU to process sophisticated artificial intelligence routines, realistic physical momentum, collision detection, and complex game logic, effectively changing the fundamental nature of interactive entertainment. The hardware graphics pipeline was now a fully independent, self-sustaining powerhouse. Despite the revolutionary nature of hardware transform and lighting, the graphics processors of 1999 still operated on what is known as a fixed-function pipeline. To visualize a fixed-function architecture, one can imagine a traditional, highly rigid factory assembly line. Raw materials, in the form of vertices and textures, are fed into one end of the line, and a series of specialized, immutable machines perform a strict sequence of operations: transformation, clipping, lighting, setup, and pixel coloring before outputting the final image to the frame buffer. While software developers had the ability to toggle specific features on or off, such as enabling fog or changing a light source, they had absolutely no ability to alter the underlying mathematical algorithms hardwired into the silicon. If a developer wanted to create a unique visual effect, such as the distortion of a heat wave, the ripples on a pond, or the imperfect refraction of glass, the fixed-function factory simply did not have the tools to do it natively. Programmers were forced to use cumbersome graphical hacks, require multiple taxing rendering passes, or abandon hardware acceleration entirely and push the workload back onto the slow CPU. The transition away from this rigid assembly line towards true hardware flexibility began in February 2001 with the release of the NVIDIA GeForce 3, a chipset codenamed NV20. Coinciding with the introduction of Microsoft's DirectX 8.0 application programming interface, the GeForce 3 ushered in the era of programmable graphics architecture. This architecture effectively replaced the rigid factory assembly line with an artisanal workshop, equipping the GPU with incredibly fast programmable processing cores. For the first time, software developers could write custom microprograms, known as shaders, and upload them directly into the GPU's execution units to manipulate geometric and visual data on the fly. This new programmability was divided into two distinct hardware stages: vertex shaders and pixel shaders. Vertex shaders allowed developers to hijack the geometry processing stage, applying complex mathematical transformations to the vertices of 3D models before they were drawn. This enabled revolutionary techniques like matrix palette skinning, which allowed the skin and clothing of a 3D character to bend, stretch, and deform realistically over a moving skeletal structure without creating ugly, disjointed seams. Following the vertex stage, the data was passed to the pixel shaders, which assumed total control over the color and lighting of every individual pixel on the screen. In the fixed-function era, hardware utilized Garot shading, a technique that calculated lighting only at the sparse vertices of a polygon and simply blended the colors across the flat surface, often resulting in muddy, inaccurate highlights. Programmable pixel shaders enabled real-time Phong shading, a much more demanding technique that calculates the exact angle of light for every single pixel individually, resulting in incredibly accurate specular highlights and incredibly realistic surface materials. The raw potential of programmable shading was famously showcased when the GeForce 3 was used to run the earliest real-time demonstrations of the game Doom 3, displaying terrifyingly realistic per-pixel lighting, and in titles like The Elder Scrolls 3: Morrowind, which utilized pixel shaders to generate dynamic, undulating water reflections. In the earliest days of programmable architecture, writing these custom shaders was an incredibly arduous task. Developers were forced to write in low-level assembly language, consisting of cryptic, hardware-specific codes that were extremely difficult to read, maintain, and debug. Furthermore, an assembly program written for an NVIDIA graphics card would not necessarily work on an ATI graphics card, threatening to fracture the PC gaming ecosystem into isolated hardware-specific camps. Recognizing that a lack of accessible tools would stifle the adoption of programmable graphics, Microsoft and NVIDIA collaborated in the early 2000s to develop high-level shading languages. NVIDIA released a language known as CG, which stood for C for graphics, while Microsoft introduced the High-Level Shader Language, or HLSL, alongside the release of DirectX 9. These high-level languages were based on the widely understood C programming language, utilizing a recognizable human-readable syntax that automatically compiled down into the complex assembly instructions required by the hardware. HLSL and CG made shader programming vastly more accessible, allowing artists and programmers to easily port their custom visual effects across different platforms, operating systems, and console hardware. As a result, the industry saw an explosion in graphical innovation, culminating in the era of smart shaders introduced by Shader Model 3.0 in 2004, which granted the GPU the ability to execute true dynamic flow control, such as conditional branching and looping logic, directly on the silicon. However, as software developers pushed the boundaries of shader complexity, a severe architectural flaw in the GPU's physical design began to manifest. GPUs of the early 2000s were built with a hard physical separation between the vertex shader processing units and the pixel shader processing units. The silicon die contained a fixed ratio of these units. For example, a graphics card might have 6 vertex units and 24 pixel units hardwired permanently on the board. This rigid physical segmentation led to massive inefficiencies because graphical workloads are highly dynamic and rarely perfectly balanced. If a game scene featured highly complex geometry, such as a dense forest of individual trees moving in the wind, but utilized very simple, unlit textures, the vertex units would be completely overwhelmed and become a bottleneck, while the pixel units sat idle, wasting immense computational potential. Conversely, if a scene featured simple box-like rooms but filled them with dense, volumetrically shaded smoke and complex particle lighting, the pixel units would choke, while the vertex units remained starved for data. This problem, known in the industry as low occupancy, meant that a significant portion of the GPU's expensive processing power was constantly being wasted. The definitive solution to this occupancy problem arrived in late 2006, marking the most profound architectural paradigm shift since the invention of hardware transform and lighting. Coinciding with the launch of the demanding DirectX 10 API, GPU designers completely discarded the concept of specialized shader units and introduced the unified shader architecture. With the release of NVIDIA's G80 architecture, which powered the GeForce 8800 GTX, and AMD's R600 core, utilized in the Radeon HD 2900 XT, the physical distinction between vertex shaders, pixel shaders, and newly introduced geometry shaders was entirely abolished. Instead of dividing the silicon into specialized roles, the unified architecture featured massive arrays of generalized stream processors. In a unified architecture, these highly flexible stream processors are dynamically allocated by an ultra-threaded dispatch processor on the fly, responding instantly to the exact needs of the software. If a frame requires massive amounts of geometric calculation, the scheduler assigns nearly all of the generalized stream processors to vertex duty. Milliseconds later, as the frame moves into the rasterization phase and requires heavy color computation, those exact same processors are reassigned to act as pixel shaders. While both major manufacturers embraced this unified philosophy to comply with DirectX 10, their hardware designs differed significantly. NVIDIA's G80 architecture utilized a highly efficient scalar processor design, clocking its individual stream processors at incredibly high frequencies independent of the rest of the chip. AMD's R600 architecture, conversely, employed a complex superscalar design based on very long instruction words. This VILW design allowed multiple mathematical operations, specifically 5 math calculations and 1 flow control instruction, to be bundled and executed simultaneously within a single processing block. Both architectures featured advanced memory integration, capable of decoupling math calculations from texture fetching, effectively hiding the latency of memory access and ensuring that the unified processing cores were never left waiting for data to arrive. The unification of the graphics pipeline ultimately transcended the realm of video games. By stripping away fixed graphical constraints and transforming the GPU cores into highly parallelized general-purpose mathematical processors, the hardware became capable of executing incredibly complex non-graphical workloads. Sensing this monumental potential, NVIDIA launched the Compute Unified Device Architecture, or CUDA, alongside its unified GPUs in 2006. CUDA exposed the staggering floating-point processing power of the unified shaders directly to software engineers, giving birth to the era of general-purpose GPU computing. The technological journey that began in the 1970s with the simple desire to offload 2D sprites and scrolling backgrounds from the CPU had steadily evolved into the creation of a massively parallel supercomputer. The Programmable Unified Architecture established in 2006 not only perfected the rendering of photorealistic real-time interactive computer graphics, but it laid the indispensable hardware foundation that continues to drive modern high-performance computing, complex physical simulations, and the contemporary explosion of artificial intelligence. Before the mid-2000s, utilizing graphics hardware for non-graphical mathematical computations, a practice known as general-purpose computing on GPUs, was a formidable and highly inaccessible challenge. Researchers attempting to accelerate complex scientific simulations, such as fluid dynamics or molecular folding, were forced to trick the hardware. They had to map mathematical problems onto graphical primitives, translating variables into pixel colors and equations into texture rendering operations. This process was incredibly inefficient, highly complex, and completely inaccessible to the broader programming community. This restrictive paradigm was permanently dismantled with the introduction of the Compute Unified Device Architecture, widely known as CUDA by NVIDIA. CUDA fundamentally altered the trajectory of the hardware by providing a parallel computing platform and a software programming model that allowed developers to use standard high-level languages like C and C++ to access the hardware's virtual instruction set and parallel computational elements. By completely stripping away the requirement to interact with the silicon through complex graphics interfaces, CUDA made massive computational throughput accessible to the mathematically literate scientific community. At the core of the CUDA programming model is a highly sophisticated hierarchy of software abstractions. The lowest level of abstraction for executing a computation or memory operation is the thread. Unlike the threads on a central processor, which are heavy and involve significant overhead to switch between, these threads are exceptionally lightweight. CUDA groups these threads into blocks and blocks into grids, allowing the hardware to dynamically schedule and execute thousands of them concurrently using a highly parallel architecture. This design excels in applications that possess inherent data-level parallelism, where the exact same mathematical operation must be applied to vast arrays of data simultaneously. The impact of CUDA on scientific computing was immediate and profound, frequently yielding computational speedups of 10 to 100 times over traditional systems for highly parallelizable workloads. Over subsequent hardware generations, the CUDA ecosystem matured to support increasingly complex execution models that eliminated computational bottlenecks. For instance, the introduction of CUDA graphs revolutionized how operations are dispatched to the hardware. Traditional execution models required the main processor to launch small kernels of code sequentially, incurring significant communication overhead. CUDA graphs allow developers to define and batch entire workflows of operations, including computations and memory transfers as a single dependency tree. This structure enforces hardware-level execution dependencies, speeds up workflow, and dramatically reduces the overhead caused by the main processor trying to micromanage the graphics processor. In modern architectures, the CUDA programming model also integrated asynchronous memory operations, allowing computation and memory transfers to overlap seamlessly. These software-level abstractions laid the critical foundation for the hardware to transcend its graphical origins and become the engine of the impending artificial intelligence revolution. While CUDA provided the vital software framework, the definitive catalyst that irrevocably fused this parallel hardware with artificial intelligence occurred in the field of computer vision between 2012 and 2016. Prior to this era, the discipline of computer vision was dominated by classical machine learning algorithms, such as support vector machines, and relied heavily on extensive handcrafted feature engineering, where programmers manually told the computer what shapes and edges to look for. Researchers utilized standard processors to train these models, as accessing parallel processing power remained highly niche. However, handcrafted feature engineering fundamentally lacked the ability to scale and generalize across the chaotic diversity of real-world visual data. Deep learning, a concept involving artificial neural networks with multiple layers, existed in theory but was largely considered an impractical pipe dream due to the lack of sufficient training data and computational power. The turning point emerged through the convergence of massive datasets and hardware-accelerated neural networks. In 2006, researcher Fei-Fei Li identified that the bottleneck in computer vision was not merely algorithmic, but rooted in a severe lack of diverse training data, leading her to champion the creation of the massive ImageNet dataset. On September 30, 2012, this dataset served as the proving ground for a deep convolutional neural network called AlexNet, developed by Alex Krzyzewski in collaboration with Ilya Sutskever and Geoffrey Hinton at the University of Toronto. Competing in the ImageNet Large-Scale Visual Recognition Challenge, AlexNet achieved an unprecedented top 5 error rate of 15.3%, outperforming the runner-up by a staggering 10.8 percentage points. This dominant victory fundamentally dismantled the viability of classical human-coded computer vision software and proved that machines could learn to recognize images autonomously. The success of AlexNet was intrinsically tied to its pioneering utilization of consumer gaming hardware. The model architecture consisted of 60 million parameters and 650,000 neurons, an architectural depth that was absolutely essential for its high predictive accuracy, but computationally impossible to train on standard computer processors. Deep learning operations, specifically the forward passes where the network makes a guess and the backward passes where it corrects its errors, are fundamentally composed of immense matrices being multiplied together. The parallel architecture of the graphics processor, originally designed to calculate the color values of millions of pixels simultaneously, proved to be vastly superior for executing the trillions of localized mathematical operations required by deep neural networks. Research from the era demonstrated that just 12 modern graphics processors could deliver the deep learning computational performance of 2,000 traditional central processors. To train the massive AlexNet model, the developers utilized 2 NVIDIA GTX 580 consumer graphics cards, each costing roughly $500 and equipped with 3 GB of video memory. These specific chips had a theoretical performance of 1.581 teraflops in standard floating point precision. However, the model's sheer size exceeded the memory capacity of a single chip. To circumvent this strict hardware limitation, the network architecture was meticulously split down the middle, with each half residing on a separate processing unit. The 2 chips processed data in parallel, and communicated across the motherboard at specific layers near the network's final output. The training pipeline established a sophisticated, highly optimized division of labor between the computer's central processor and the parallel graphics processors. While the parallel hardware executed the computationally intensive forward and backward math passes, the central processor was utilized for continuous on-the-fly data augmentation. The central processor handled tasks like loading raw images from the hard drive, scaling them to 256 pixels, cropping them into 224 by 224 patches, applying horizontal reflections, and normalizing pixel color values. Because these operations occurred concurrently with the mathematical training, they were essentially computationally free and ensured that the parallel hardware was never starved for data during the 5 to 6 grueling days required to train the model over 90 complete passes of the dataset. The network utilized specific techniques like dropout to prevent overfitting, and the final competition submission actually utilized an ensemble of 7 distinct models to maximize accuracy, further highlighting the massive computational requirements of the project. The AlexNet victory triggered a permanent, industry-wide pivot. By 2015, hardware-accelerated deep neural networks dominating the ImageNet competition had actually surpassed human-level accuracy in image recognition. Deep learning rapidly transitioned from an academic curiosity to a fundamentally new software model, wherein computer programs were no longer sequentially coded by human engineers, but rather learned autonomously by billions of software neurons iterating over trillions of connections. This sudden realization catalyzed a permanent shift in how hardware manufacturers approached silicon design, realizing that the future of all high-performance computing lay in highly parallelized deep learning acceleration. As deep learning and advanced graphics rendering matured simultaneously in the years following the ImageNet breakthrough, the mathematical requirements for these two domains began to aggressively diverge. Graphics rendering increasingly demanded complex geometric calculations and highly accurate light simulation, while artificial intelligence training required massive throughput for low-precision matrix multiplication. In response to these conflicting demands, hardware architecture evolved from relying solely on uniform programmable shader cores to incorporating highly specialized, distinct hardware logic blocks on the exact same silicon die. This architectural bifurcation was formally introduced to the world with the launch of the NVIDIA Turing architecture in the fall of 2018. The Turing architecture introduced a revolutionary concept known as hybrid rendering, which combined traditional polygon rasterization, real-time hardware-accelerated ray tracing, and artificial intelligence-driven image enhancement into a single cohesive processing pipeline. To achieve this unprecedented fusion, the architecture introduced two entirely new classes of hardware accelerators, the ray tracing core and the tensor core. Real-time ray tracing, the physical simulation of how light paths travel, bounce, and create physically accurate shadows, reflections, and refractions, was long considered the holy grail of computer graphics. For decades, it was utilized exclusively in Hollywood film production, where massive server farms would take hours to render a single frame of video, and it was deemed computationally impossible for real-time applications like video games. The primary computational bottleneck in ray tracing is determining exactly where a ray of light intersects with a three-dimensional object in a virtual environment. Doing this naively requires mathematically testing a single ray against millions of individual triangles in a digital scene. To optimize this, software developers utilize a bounding volume hierarchy, which is essentially a massive, complex decision tree structure that encapsulates highly detailed geometry inside larger, simplified bounding boxes. These boxes are recursively subdivided into smaller and smaller boxes until the individual geometric triangles are finally reached. When a computer tries to traverse this tree using standard general-purpose parallel TORs, it performs abysmally. Ray tracing algorithms are inherently divergent. Adjacent rays of light may bounce off a bumpy surface in completely different directions, resulting in highly unpredictable memory access patterns that destroy the efficiency of standard parallel thread execution. To solve this specific bottleneck, the ray tracing core acts as a dedicated, specialized coprocessor designed exclusively to accelerate the traversal of this bounding box tree and perform the final ray triangle intersection tests in hardwired silicon. When a program casts a ray using modern application programming interfaces, the hardware immediately hands the mathematical traversal of the tree over to the ray tracing core. The core evaluates the bounding box intersections, rapidly navigates the tree hierarchy, and performs the precise mathematical intersection test against the geometric triangle, subsequently returning the exact hit data to the standard processing cores. By offloading this highly irregular, mathematically intense workload to fixed-function silicon, the core frees the standard programmable cores to focus on shading and logic, accelerating ray tracing computations to up to 10 billion rays per second in the initial Turing generation, and bringing cinematic lighting to real-time applications. Simultaneously, the Turing architecture introduced tensor cores to address the unique and massive mathematical demands of deep learning. While traditional processing cores are highly versatile scalar processors that execute serially, one operation at a time per core, and are heavily optimized for standard 32-bit or 64-bit floating point math, tensor cores are explicitly engineered for one thing: massive matrix multiplication. The absolute fundamental operation in neural network training and inference is the multiply-accumulate operation, which involves multiplying a data input by a learned weight and adding it to an accumulator bias to carry the data forward. A tensor core executes this entire complex operation for a small grid of numbers, such as a 4x4 matrix, in a single hardware clock cycle. By integrating fused multiply-accumulate units directly at the physical hardware level, tensor cores achieve a computational throughput that exponentially exceeds that of standard cores for computationally dense artificial intelligence tasks. Furthermore, hardware engineers realized that deep learning models are inherently resilient to mathematical noise. They simply do not require the extreme, painstaking decimal precision of 64-bit or even 32-bit calculations to achieve high predictive accuracy. Consequently, tensor cores were engineered to support automatic mixed precision training natively in the hardware. They can ingest raw data inputs in much lower precision formats, such as 16-bit floating point or even 8-bit integers, perform the rapid matrix multiplication at blistering speeds, and then accumulate the final result in a higher precision format to prevent numerical underflow or rounding errors. In modern workflows, the general-purpose cores and the tensor cores act completely synergistically. The tensor cores handle the incredibly heavy matrix multiplications of the neural network passes, while the standard cores execute element-wise operations, activation functions, and data pre-processing. By separating these heavily conflicting workloads into dedicated silicon pathways, the hardware permanently evolved from a monolithic rendering device into a heterogeneous, highly specialized compute platform. As the focus of the global artificial intelligence industry shifted away from recognizing images towards understanding and generating natural human language, the underlying neural network architectures transitioned almost entirely to the transformer model. These models exhibit a unique property regarding scale. Adding exponentially more parameters and training them on vastly more data directly yields superior reasoning and generative capabilities. Consequently, large language models ballooned from millions of parameters to hundreds of billions of parameters and eventually trillions of parameters, triggering an unprecedented global arms race for compute resources. The generative artificial intelligence boom became fundamentally compute-bound, creating a landscape where the primary limiting factor for commercial success was simply access to vast quantities of highly optimized silicon. The sheer cost and time required to train these massive linguistic models necessitated the development of processors designed exclusively for the data center, abandoning graphical rendering outputs entirely in favor of maximizing raw arithmetic throughput and memory bandwidth. This enterprise data center era is defined by architectures such as NVIDIA's Hopper and Blackwell. The Hopper architecture, featuring the highly sought-after H100 chip, introduced the industry's first dedicated transformer engine, which dynamically applied 8-bit floating-point precision to dramatically accelerate transformer models while carefully preserving mathematical accuracy. However, as language models continued to scale at an exponential rate, the industry required yet another hardware paradigm shift, which materialized in the Blackwell architecture, encompassing chips like the B200 and B300. The Blackwell architecture represents the absolute pinnacle of current data center hardware, constructed using a revolutionary dual reticle design. Because modern semiconductor fabrication has pushed photolithography to the absolute physical size limits of a single silicon wafer print, known as a reticle limit, engineers designed the Blackwell processor by manufacturing two incredibly massive distinct dies and stitching them together with a custom power-efficient connection technology called the high bandwidth interface. This microscopic bridge delivers an astonishing 10 terabytes of bandwidth between the two halves. Fabricated on the absolute cutting-edge manufacturing nodes, the combined chip boasts a staggering 208 billion transistors, more than double its predecessor, yet functions seamlessly to the software programmer as a single unified accelerator. At the microscopic architectural level, Blackwell introduces the 5th-generation tensor core, specifically engineered to support an even smaller mathematical format known as 4-bit floating-point precision. To squeeze maximum possible throughput out of modern language models, engineers intentionally sacrificed traditional high-precision supercomputing math, dropping 64-bit performance drastically to heavily over-index on these ultra-low precision formats. The 4-bit tensor cores provide an astonishing 14 petaflops of raw compute power on a single chip. Utilizing these extremely low precision formats acts much like aggressive file compression. A model quantized to 4-bit precision requires less than half the physical memory footprint of standard formats, fundamentally reducing the severe bottlenecks associated with loading immense language model weights into active memory. The resulting performance gains are generational. Verified performance data demonstrates that these platforms deliver up to 11 to 15 times faster large language model throughput per processor compared to the prior generation. In standardized benchmark testing across the industry, massive clusters of these chips achieved more than triple the training performance on models exceeding 400 billion parameters. Furthermore, recognizing the massive commercial value of these proprietary models, modern enterprise chips introduced the industry's first trusted execution environment with input-output capabilities, enabling confidential computing. This cryptographic feature allows corporations to securely train massive models and protect sensitive intellectual property without sacrificing the massive throughput performance required. Despite the astronomical exponential increase in the sheer computational capacity of these processing units, a severe physical bottleneck threatens to limit overall system performance: the memory wall. The issue was predicted decades ago, but has reached a critical breaking point in the artificial intelligence era. Over the past 20 years, while the peak compute power of hardware has scaled incredibly rapidly at a rate of roughly 3 times every 2 years, the underlying memory bandwidth required to feed data into those processors has only scaled at a rate of 1.6 times every 2 years. This widening discrepancy dictates that modern artificial intelligence workloads are rarely actually compute-bound, they are predominantly memory-bound. Dense matrix multiplications may run in a single clock cycle on a tensor core, but the physical time it takes to move the data from the memory modules across the circuit board to the processor registers starves the system. Operations like batch normalization or simple activation functions feature very low arithmetic intensity. They perform very few mathematical operations per byte of memory accessed, causing the massive computational engines to sit completely idle while waiting for data to arrive. To breach this memory wall, the industry was forced to completely transition away from standard computer memory and adopt high-bandwidth memory for enterprise applications. Consumer graphics cards and edge devices continue to utilize standard planar memory, known as Graphics Double Data Rate 6, which provides excellent speeds and a reasonable balance of performance and cost for video games. However, this standard memory is planar. The chips are spread out flat on a printed circuit board surrounding the main processor. This physical distance requires higher electrical voltage to drive signals across relatively long physical traces on the board, generating significant heat and consuming excessive power. It operates much like a very fast but fundamentally narrow highway. High-bandwidth memory mitigates these physical constraints through a revolutionary three-dimensional architectural redesign. Rather than spreading memory chips out on a flat board, this technology vertically stacks the memory dies directly on top of one another. These stacked layers of silicon are intricately interconnected by microscopic vertical wiring running straight through the chips, known as through-silicon vias. The entire vertical memory stack is then placed incredibly close to the main compute die on a foundational layer called a silicon interposer, drastically shortening the physical distance the electrical data signals must travel. The defining characteristic of this technology is its ultra-wide memory interface. Where a standard memory interface might be 256 or 384 bits wide, high-bandwidth memory utilizes a massive 1024-bit or wider bus. This allows the processor to move gigantic volumes of data in parallel, achieving enormous bandwidth even at lower memory clock speeds. Because it operates at these lower clock speeds and utilizes drastically shorter physical traces, it is exceptionally power efficient, operating at roughly 1.2 volts compared to the higher voltages of consumer memory. This combination of vertical physical density, ultra-wide bus architecture, and low voltage allows data center processors to feed their compute engines with minimal latency, operating like a sprawling superhighway with thousands of lanes. The progression of this memory technology has desperately tried to keep pace with the scale of language models. While the previous generation featured 80 gigabytes of capacity, yielding roughly 3.3 terabytes per second of bandwidth, the newest architectures integrate 192 gigabytes, capable of pushing an astonishing 8 terabytes of data per second. Future iterations project doubling the interface width yet again, to ensure that incredibly high parameter models and long context inference engines are not choked by memory constraints. The final piece of the modern artificial intelligence architecture is the interconnect fabric. Trillion-parameter language models simply cannot fit into the physical memory of a single processor, nor can they be mathematically processed by a single server node within reasonable timeframes. Training and running these massive linguistic architectures requires distributing the workload across hundreds or often tens of thousands of separate processors working in perfect unison. Traditional computer servers utilize the peripheral component express bus for component communication across the motherboard. However, this standard bandwidth is vastly insufficient for the massive constant data synchronization required by deep learning, severely throttling efficiency when multiple processors attempt to share data. To solve the interprocessor bottleneck, engineers developed specialized high-speed proprietary interconnects designed to provide seamless, incredibly low-latency data movement. The evolution of these interconnects, such as NVIDIA's NVLink, perfectly mirrors the exponential growth of neural networks. While early iterations provided modest uplifts over standard motherboard connections, the modern 6th-generation technology enables an astonishing 3.6 terabytes of bidirectional bandwidth per single processor. This speed is over 14 times the bandwidth of the absolute fastest standard connections available, effectively removing the physical bottleneck and ensuring that data pathways do not starve the computational throughput of the tensor cores. However, incredibly high point-to-point bandwidth between two chips is insufficient for the highly complex communication patterns inherent in modern architectures, particularly mixture of experts models, where pieces of language are dynamically routed to different expert subnetworks residing on entirely different hardware racks across a data center. To address this massive logistical challenge, the interconnect ecosystem relies on dedicated networking chips that facilitate non-blocking all-to-all connectivity across dozens of processors. By deploying these advanced network topologies, the architecture of the modern supercomputer has completely shifted away from individual server nodes to the concept of the rack-scale supercomputer. Modern liquid-cooled server racks integrate dozens of processors inside a single massive cabinet. Connected by these high-speed switches, 72 separate processors can operate functionally as a single massive unified brain, boasting up to 260 terabytes of aggregate bandwidth between them. Furthermore, the physical network fabric itself has evolved to actively participate in the mathematical computations of artificial intelligence training. In large distributed server clusters, deep learning requires the constant mathematical synchronization of weight gradients across all participating processors. Moving massive data matrices across the network cables purely to add them together on the processors wastes immense amounts of time, compute power, and bandwidth. Modern networking components now include hardware engines for protocols like the Scalable Hierarchical Aggregation and Reduction Protocol. This technology enables in-network computing, where the network switches themselves actually intercept the data packets as they fly through the cables, perform the necessary mathematical addition operations internally inside the switch, and broadcast only the finalized condensed results back to the processors. This offloads critical communication overhead from the tensor cores, optimizing the efficiency of the entire data center. Together with complementary network interfaces, these interconnects allow enterprises to scale training clusters to tens of thousands of processing units without encountering the debilitating latency penalties that would otherwise grind large-scale artificial intelligence research to a complete halt. The transformation of the graphics processing unit from a highly specialized visual rendering peripheral into the absolute backbone of the global artificial intelligence infrastructure stands as one of the most significant engineering achievements in modern computing history. This evolution was never driven by a single sudden breakthrough, but by a continuous, relentless cycle of software abstraction and highly specialized hardware divergence. The software abstraction democratized parallel processing, enabling the hardware to be utilized by data scientists instead of just graphics programmers. This laid the immediate foundation for the deep learning catalyst, which conclusively demonstrated that highly parallelized silicon was the absolute optimum architecture for simulating neural networks. As the demands of photorealistic graphics and artificial intelligence began to aggressively conflict, the silicon bifurcated its internal architecture, introducing dedicated cores to untangle the chaotic math of ray tracing and separate cores to execute massive, low-precision matrix multiplications in a single clock cycle. Today, the technology has fundamentally outgrown the physical confines of the individual computer workstation. The insatiable demands of large language models have necessitated the creation of the data center scale processor. As the entire industry actively grapples with the physical limitations of the memory wall, innovations such as three-dimensionally stacked memory and microscopic die-to-die interconnects ensure that the computational engines are continuously fed with data. Furthermore, the deployment of intelligent network fabrics that actually perform math as data moves through the cables have transformed the very definition of a computer. A modern artificial intelligence supercomputer is no longer a collection of discrete parts, but a unified, rack-scale entity operating in perfect orchestrated synchronicity. The architecture remains the singular foundational technology underpinning the future of cognitive computing, continuously and rapidly adapting to the insatiable mathematical demands of artificial intelligence.